Here we will look at yet another method of computing determinants called Cofactor expansion. Let's imagine a square matrix of arbitrary size n having coefficients like that. The determinant, according to this Cofactor expansion, can be always written as a sum of elements of the matrix taken from a fixed row or a column. Let's imagine row number I. So I is fixed, j is a position in the row, it changes for all possible values from the first to the last. And then each such entry has to be multiplied by a quantity which is called cofactor. So this is the Cofactor expansion. The interesting, of course, bit is a cofactor. Number ij is a few things. First of all, a sign, which is easy to compute. It's just controlled by the parity of I plus j, times the determinant. So we're trading one determinant for many, but the trade is in the size, because this determinant will be size 1 less. And the determinant is of the original matrix without row I and column j. That means that we take all the matrix entries which are not in row I and column j, and these are the four corners which we compress into a matrix of size 1 less, and compute its determinant. So if we call this matrix, I think it's called M, for minor Mij, usually its matrix entries, I'll call ij twiddle, they are, this process of compacting makes them like that. So they are original matrix entries if both, if we are in this first corner, meaning that if, I'm using the same I and j, so maybe I'll call it ij, and the entries are s and t. S and t are arbitrary indices. So if s is less than I and t is less than j, we are in this corner, we don't change the indices. If we are in this corner, that means that we are still with s less than I, but t becomes larger than j. We have to compact, meaning that we have to not count this one, again, meaning that we're subtracting, shifting t by 1. If we are in this corner, s is larger than I, but t is less than j, and we are in the process of compacting, we are shifting s by 1. And finally, if we're in this corner, to compact it to a matrix, we have to shift both s and t by 1. That is when we have these conditions on s and t. So that is the general procedure, which reduces determinant of size n to a sum of determinants of size n minus 1, but we'll have n of them, and we have to compute them, multiply by signs, multiply by corresponding matrix entries, take the sum. That's a way of seeing the determinant. So about the proof, let me look at the more concrete situation for simplicity, assuming that my so this is Cofactor expansion alone row I. Let me assume that row is number 1, and then I will just have the sum of matrix entries multiplied by their cofactors, and they are all taken from row 1. This is 1, 2, rather. So that is the answer for row 1, first row cofactor expansion. It doesn't matter which row I take, or if it is row or column, the same formula will work for columns. It doesn't matter, the proof will still be the same, but that is something which makes it more concrete. So in the determinant, we have sums of products of matrix entries labeled by permutations. The structure of the determinant is controlled pretty much by permutations. So that's what I will be using to see this decomposition of the determinant into the sum, like that. I will be separating permutations into groups corresponding to the summands. So here permutations will be those which are mapping 1 into 1. Here the permutation will have to satisfy the condition like that all the way to the last bunch of summands where permutations will be mapping 1 into n. It's just so that we will have the first of the factor in the determinant product being what we want. And the rest will be just giving us these cofactors. That's the essence of the proof. But to get to completely the answer, we will have to first analyze this procedure of compacting. When we compact, we rename positions of our matrix entries because we want to make matrix, so seamless matrix of size 1 less. So we are shifting the components, the positions of the matrix by 1 sometimes. So that is really making sense, is possible to make sense on the level of permutations. Here permutations are not moving 1 around, 1 is a fixed point, they're moving the rest, and then the rest we can identify. So it's basically renaming elements which we are moving around for these permutations, identifying them with 1 up to n. So sigma is moving this into the same set, and we are just shifting all by 1. That's what we are doing. So that is the case where we have no corners in here. This is the only corner we have. Since we are looking at the cofactor expansion along the first line is here. So we are in general having just 2 corners to compact. And that is the extreme case where we just have 1 corner only. And so yeah, that is the situation like that. We have first row and first column, and all the rest is our matrix, but it starts with 2 and goes to the n. Instead, if we write the formula for the determinant, we are using label 1, 1 here, so we have to shift it all. We have to turn the permutation sigma into permutation of n-1 first numbers, and the rule is like that. So we are, for this new permutation, we have the following easy rule. And the sign, it's easy to see the sign of this permutation of n-1 things is the same as the sign of the permutation original. So progressing to the next bunch of matrix products corresponding to permutation satisfying this condition, here sigma moves the set to all the way to the n into the set of 1 consisting of 1, 3, and then all numbers to the n. So this is all the numbers not equal to 1. These are all the numbers not equal to 2. And so again, we have to turn this permutation into permutation of first n-1 numbers. The rule is, well, is before. If sigma of I is not 1, and it is just if rather sigma of I plus 1, if sigma of I plus 1 is 1. So this time the sign of this reshaped permutation is opposite to the sign of sigma. And all the way through, it will be seeing the change in sign each step we make. It's simply because this set can be made as equal to that if we just swap 1 and 2 informally. That is costing us -1 sign, so one swap. So we're sort of precomposing this permutation when with the transposition 1, 2, we're changing the sign. Next time we will have permutations moving numbers between 2 and n into numbers between 1 and n not equal to 3. And again, this set can be made the same as this by a simple transposition. So each time we move, progress to the next case, we are effectively moving by transposition, and that creates an alternating pattern of signs. So each next relation between original permutations and new will be different to the previous one by a sign. So that is basically it. Now we can look at the proving this expansion. We can look at the formula for the determinant, for the definition. As a sum for all permutations, and then group them, group those summands into these n cases. So that will be basically fixing the first, and then looking at the rest of the summands, sorry, the rest of the factors in the product. And that, of course, with a sign of sigma, and then rewriting the entries according to this rewriting rule, we will have so that will be becoming 1, and that will become n minus 1. And then sigma will turn into this sigma twiddle. And the sign, original sign, can be swapped to sign twiddle with the price, which is -1, controlling this alternating pattern, -1, 1 plus I. And so we have the cofactor. That is nothing but the cofactor 1i. And yeah, we have a proof of the special case, but the general case is no difference. Let me illustrate this computation method by looking at an example. The cofactor expansion is particularly useful when we have zeros. And the more zeros we have in the row, the better the cofactor expansion becomes, because zero entries in the row will really minimize our, reduce our computations of cofactors. We don't need cofactors for 0 entries. So let's imagine a matrix with 2 zeros. Something like that. And then cofactor expanding along the first row, we will have -1 times its cofactor, and then +1, this entry times its cofactor, and that will be it, no third term. So the cofactor here, the cofactor for this element, will have the sign, which is plus. The cofactor for this entry will have the sign, which is minus. And then here we'll have the determinant of whatever is left after erasing the first row in the first column, namely this corner matrix, -1, 1, 1, -1. And for the second cofactor, the determinant will be when we block take out the first row and the second column. So these will be the 4 entries left. 1, 1, 0, -1. Now the task is to compute these two 2x2 determinants and do the arithmetic. The first determinant is 0 because the rows are proportional. So we can take elementary transformation, for example, of row addition, take the first row added to the second, and in the process annihilate the second row, make it 0, 0. The determinant doesn't change, but in the new form it will be manifestly 0. Or we could just compute it by the formula, so this product minus that product, and it also gives us 0. So this term just disappears, and we'll be looking only at the second term, which has a sign -1, and then the determinant is also -1, and so the product is 1. Again, it's good to verify the answer by doing computation some different way. We could do it using elementary transformations, and the first move is, assuming that it is our pivot number 1, is to get rid of this, so that will be possible to do by row addition. Row 2 plus row 1 will make matrix look like that. And then we could get it to triangle shape by doing column transformation. So swap of columns 2 and 3 will make it, I'm sorry, not columns, rows. Why columns? Row swap, swapping the 2 will make it triangular. That is it. It doesn't match up. Let's check what is done in the process. But yeah, of course, it doesn't match up because I forgot to pay the price for the row swap. The determinant has to change its sign between this and that. And finally, the determinant of this is just the product of diagonal entries, because below the diagonal I already have zeros. So I have with negative sign the product, which is again -1. And the answer is 1 again. And matching means that most probably computations are correct.